Yeah, thank you, Lenka. So yes, I'm going to talk to you today about a recent work that we did with Florent, Lenka, and Bruno, a postdoc in our group, on the phase retrieval problem. So it's basically quite a classical paper in a sense that we use all the traditional machinery of statistical physics to apply to inference problems, to investigate a bit what are the limits of the phase retrieval problem. So to begin with, let me consider a very generic problem that we have heard a lot about this week, which is a generalized linear model. So I'm going to consider the following setting here. I have this signal vector x star that I'm trying to recover, which is in n dimension. And what I have is the observations y mu, which are given by possibly noisy observations of the matrix vector product of phi and x star. So phi is modeling the data matrix, and phi and x star can be both real or complex variables, and I have m observations, and the signal is in n dimension. So when you state a GLM like this, what makes the phase retrieval special is only that the channel distribution is a function of the modulus, or the absolute value, of the matrix vector product inside. Right? So this is kind of the most generic way to state the phase retrieval problem. And even in the noiseless case, so when you directly observe this modulus, this problem is highly non-trivial, and there's been a lot of different approaches to tackle it, from spectral method, SDP relaxation, or method from non-convex optimization. Here our goal is quite a bit different. It's to understand what are the fundamental limits of this problem in a random setting, but in a typical setting, right? When if you consider random data and the random signals, what is the typical performance that you can achieve? And for those who are maybe more familiar with the phase retrieval literature, this is quite different from some studies that focus on the worst case bounds. And as we will see, we will get different results actually. Okay, so let me come back to this generic GLM. And so as I mentioned, we want to understand the limitations of this problem. So these are the kind of questions we ask, right? How, in the high dimensional limit, how much data do we need to recover the signal at least partially or perfectly, and with which algorithms? And okay, these are the four main hypotheses of our model, which we're trying to stay as generic as possible. So variables can be real or complex. I have this beta factor, which is 1 in the real case and 2 in the complex case. I have a prior distribution on the signal with a variance rho. And the two most important hypotheses are on the data matrix. The first one is that its right eigenvectors are completely delocalized. So basically, it's orthogonally invariant on the right. And that its singular value distribution converges, right? So these two hypotheses actually encompass the majority of random matrix models that you can think of. For instance, Gaussians, product of Gaussians, random orthogonal matrices, and more generically, I mean, you can engineer a model to have any distribution that you want. Okay, and so, I mean, our first result, as is classical for us, is a conjecture based on the replica method, okay? And it's basically the most maybe simple way to state this is to say that there exists a scalar optimization problem on two variables involving the sum of three functions, which are fully explicit. It's just a bit lengthy to write, and which decompose quite nicely depending on the features of the problem, right? So you have one function which depends only on the prior, the other one only on the channel, and the last one only on the spectral distribution of the data. And the claim is that if you can solve this scalar problem, then you can obtain the information theoretic MMS, right? And okay, so this is already a conjecture. Now the first thing we can ask is, can we prove this, at least in some cases? And there are two cases in which we can. The first one is if the data matrix is Gaussian. So in this case, the real case was already known in this paper by Jean, Barbier, and others. And so we basically extended this to the complex case. And there's another case in which we can prove this, is if the prior on the data is Gaussian, and the data on the matrix is the product of a Gaussian and another thing, right? Which can be random or deterministic or anything. In these two settings, we can prove the above conjecture, and this is based on the methods that were mentioned by Florent in his lecture, in his first lecture, and these adaptive interpolation methods that were in particular developed by Jean Barbier and others recently. Okay, so before diving more specifically into phase retrieval, let me mention a few other things on the algorithmic, other things we can say about algorithmic properties of this problem. again, based on the replica method, so this is not new for people who know a bit about that, is that once we have this variational problem that we call replica symmetric potential, we know that this, there's a big conjecture that the optimal polynomial time algorithm in terms of recovery is based on approximate message passing, right? And these kind of algorithms have been studied a lot in the past years. And they have also a very nice property, is that we can study the performance analytically, right? And we can do it by looking at the same replica symmetric potential. And the claim, which is not a claim in this case, it's a theorem, is that the error achieved by the algorithm is basically given by this potential, but instead of taking the global supremum, you take the local supremum that you attain by starting from the solution where qx equals qz equals 0, which corresponds actually to a random initialization. Okay, and this is very nice because then just by studying this scalar problem, we can get many things, we can get many properties of our problem. For instance, we can study the existence of statistical gaps just by looking if there are some local minima in the landscape. Okay, so now let me go to phase retrieval. So here, for this slide, I'm not going to restrict myself a lot. I'm just going to assume that the channel only depends on the modulus of the absolute value. And I'm interested in the weak recovery problem. How much do I need? How much data do I need to beat a random guess, right? And we have actually a precise answer for this, which is this formula. Okay, so this threshold is a solution of this equation. So this equation is actually not explicit. I mean, all these terms can depend on alpha as well. So in general, you have to solve it. And again, we derive it by looking at the replica symmetric potential. And a first very simple consequence that you can draw from this formula, which is quite interesting, is that the spectrum of the data actually enters only here and here, but here it's just the first moment, so it's basically a global scaling. And so in order to maximize this, you must take a delta distribution, which means that in phase retrieval, for any channel on prior, the highest weak recovery threshold is always going to be given by orthogonal or unitary matrices. And this is some fact for which we don't really have a good interpretation, but which comes very naturally from our results. And if you specialize this formula to the noiseless phase retrieval case, of course, it simplifies a lot, and you find back some results that were found for specific case of matrices in the literature. Okay, so now let me go precise even more my problem. I'm considering noiseless phase retrieval. And I'm interested in the strong recovery problem. When can I perfectly recover the signal? And okay, at least as best as I can, right? Because there might always be a part that you cannot recover because the data matrix might not be full rank. And again, we have a simple answer for this, is that if R is the number, is basically the fraction of non-zero singular values of phi, then the threshold is given by beta times R. So in particular, so recall that beta is 1 in the real case and 2 in the complex case. In particular, it does not depend on the statistics of the matrix. And a funny thing about this formula is that actually in the real case, you can derive it by a simple counting argument, which was, I think, first mentioned for compressed sensing in this paper, and which basically is, I mean, the main idea is very simple, is that if you know a real vector, the absolute value of a real vector, basically you can try all the signs, right? It's exponentially long, but you can always recover the vector. In the complex case, however, you cannot do that, because if you know the modulus of a complex number, of course, there is infinitely many possibilities. And so as far as we know, the fact that the threshold is equal to 2R can only be derived with our replica symmetric analysis. Okay? And let me now present, before ending, two simple applications in the noiseless phase retrieval case. So I'm going to consider two different matrices. The first one is the complex Gaussian matrices. Second one is unitary matrices. And okay, the blue curve is the performance predicted, the predicted performance for the optimal algorithm for approximate message passing. And the orange curves are the information theoretic MMSE. Right? And the points are explicit simulations of the algorithm. So we can already see a few things. First, I mean, the points are in really good agreement with the predictions. And also in both cases, you have, as mentioned, there exists a statistical to computational gap, right? Which is actually quite big in the unitary case and quite small in the complex Gaussian case. So in this phase, in this science phase regions, we don't know how to recover the ITM-MSE in polynomial time. And okay, and there are, let me just cite a few of other consequences that we have in our analysis. For instance, in the unitary case, you can see that the orange curve drops brutally from 1 to 0. It's basically a step function. And this is sometimes denoted as an all or nothing transition because you either recover nothing or everything. And an interesting phenomenon is that this thing usually appears in sparse problems, and this is a dense problem. And also, we can show with our equations that this only appears for unitary matrices. For all of the complex matrices, this will not be the case. So this is, again, something which is, for which we don't really have a good physical interpretation, but it's a funny prediction. And maybe a last thing is that if you look in the unitary case, we also try to run the algorithm on some Fourier matrices. We added a bit of randomness by shuffling the columns, and then we see that the algorithm performs basically as well as for uniform unitary matrices. So we can allow for some kind of control structure. And let me finish by simply this table, which is okay, which is a bit big, but basically the new results are in red, and I'm giving the different thresholds for different setups. And I think it summarizes quite nicely the goal of our work, which was to unify many different previous results and extend them when we can in a global framework, which allows to encompass all of them. And I think I'm done. Thanks.
Thank you. Do we have questions for that?
Yeah.
You have a factor of 2 difference between the real case. I have to keep the last?
Yes.
For the perfect recovery threshold.
Between the complex and the real case, right?
In the perfect recovery threshold, yes.
Does it have anything to do with the fact that the complex is quite small?
But I don't know. I mean, I don't really have an yeah, because as I mentioned, in the real case, you have a counting argument to derive this. In the complex case, even if it's, I mean, twice as big, basically, I mean, it's R2, we don't have this counting argument. Because, I mean, absolute value and modulus is not really the same thing, right? So I don't know. It's hard to tell. I mean, it's actually not a silly question. It's a good question, I think. Yeah.
Another question: how much do you lose by taking the modulus compared to consistent things?
What do you mean? How much do you lose?
So now you want to recover the signals.
Yeah.
In one case, you take the modulus. In the
Yeah.
other, you don't take the modulus. And so you get the curve for both.
Yeah.
And do you know how much you lose?
Like, okay, comparing the MSEs of just removing the, but I mean, how do you define? Because if you take the modulus, the channel is a function of a real variable. If you don't take it, it's a function of a complex variable, right?
Well, you could observe a complex variable, or you can just take the real case.
Yeah, you can do the real case. I don't know. I don't know how it compares in the real case. Basically, say the compressed sensing linear case, modulus versus non-modulus. So, I mean, absolute value versus linear. I don't know.
I think we have some plots for the Gaussian matrices, the real valued case in our paper, comparing the two.
In which paper?
The one with Jean.
Okay, yeah, the one with Jean, Leo, yeah, maybe. Because as I mentioned in the paper of Jean, Leo, etc., they had the GLM for the real case with Gaussian matrix, and in this case, apparently they studied it.
So you can lose a lot in the sense that, for instance, if your signal was sparse, then compressed sensing really very few measurements, like basically of order of the sparsity. But this weak recovery threshold that is at half actually stays at half even for sparse systems. So in the sparse system, you really lose like a linear factor in the really a lot. In other cases, not so much. It really depends. Like there will be whole zoology corresponding to this table. You know, if you're interested in particular cases, we could.
Yeah. Yeah.
Maybe it's a dumb question, but can this be used to look for phase retrieval in protein crystallography or X-ray crystallography? Like how many samples you need?
Yeah, I think it can. I think it's more okay. I think Jonathan is more of an expert on this than me.
Yeah, I think crystallography is about F, like the full crystal.
Yeah. And yeah, as I mentioned, we try to, I mean, we have some, not this is another slide. Here you have these points. I mean, some of them, okay, so for instance, these ones are actually done for Fourier matrices, right? But we need to add some randomness. We need to shuffle the columns. If we take the basic, if we take the pure Fourier matrix without changing it, the algorithm does not work as well.
Okay, can the next speaker come to change the computer?
Yeah.
Well, maybe there is the last question, or?
Yeah.
If I just-
I had only dumb questions apparently, so. Is optimum.
But then I was thinking, okay, but can I try can one try to change, I don't know, the short function or things like that by hand, I don't know, just to try to improve.
I don't get the question. You want to improve recovery with changing?
Yeah, I mean, in the end, there's still a conjecture that you have this fucked up. I mean,
Yeah, of course. I mean, you could. I don't have a hard proof.
algorithms that can enter.
Yeah.
But, I mean, just starting from A and P to back to,
Yeah.
I don't know. I mean,
But changing the scheduling function is not helping you. This
yes, this
Ça marche quand même, ça?
Non, c'est pas celui-là.
Ah, c'est pas celui-là.
c'est difficult.
C'est ça?
Oh, ça c'est pour le laser et ça c'est pour changer les scènes.
Ok.
Okay, the next talk is by Cedric on the asymptotic subgeneralized linear models beyond Gaussian matrices.
Hello everyone. So I'm going to present joint work with Aya Barra and Florent Zacala, and so asymptotic errors of generalized linear models beyond Gaussian matrices. So essentially what I'm going to present now is a big proof of a replica formula. And so instead of giving a lot of technical details which would surely bore you, I'd like to introduce some background and make so that the sketch of proof appears naturally. So we've had many proofs, notably that has been presented by Florent, amazing work by Antoine. I'd like to show you something a little bit different. Okay, so just very simple setup. I'm going to be looking at supervised learning, so learning from labeled examples. My input space I will denote A, R to the power n, for example. My output space Y, -1, 1 for classification, big R for regression. And I have a training set, input-output pairs, classic stuff, as you all know. And my goal is to estimate a function little h going from A to Y to predict new outputs, which I want to train on this training set, classification, regression. So let's choose a parametrization. So let's keep it simple, as I said. Convex generalized linear models. So I have a nonlinearity G that quantifies the loss, the error that I'm making on a given linear prediction A transpose X with respect to the given label Y. And I have a regularizer F. So I'm placing myself in this so-called teacher-student scenario, with, which you are all familiar with now from the lectures that we had. So I'm going to assume that the labels Y are pulled from a degenerative model of the following form, a nonlinearity phi of the data matrix A times x0, which is an underlying ground truth, pulled from any well-behaved distribution. Now, I'm going to allow mismatches between phi and the generalized linear model, which is the so-called non-Bayes optimal setting. And so, for example, this is different from what Antoine just presented, which is a Bayes optimal setting. And so here, for the remainder of this talk, I'll place myself in the high-dimensional limit. Again, classic stuff in statistical physics of learning. M and n go to infinity with a fixed ratio alpha. So a few examples. This includes linear regression, ridge, lasso, elastic net, logistic regression if you want to do classification, linear support vector classifier if you are looking for a max margin solution with a hinge loss. Now, the objective that I'd like to do is to quantify how good the regression is, and to do so, I'd like to evaluate 3 key order parameters. So rho 0, which is the square norm of x0. So here in the teacher-student scenario, this is given. Q star, which is the squared norm, limiting squared norm of the estimator x star that I'm producing with the GLM. And then M star, the asymptotic overlap between x0 and x star. Okay, so these three quantities are important because I can reconstitute the mean squared error, which is the relevant quantity for regression, or I can reconstitute the reconstruction angle, which is the relevant quantity to study the performance of classification since I'm looking for a separating hyperplane. Okay, so now how is this typically done in statistical physics of learning? So I prepared these slides before last week, so I'm sure now you all know how this is done in statistical physics of learning. The cost function is just a Hamiltonian. I'm forming the partition function, the structure of which will depend on H, so what did I choose for G and F? And then what type of randomness do I allow for the matrix A? Is it an ID Gaussian? Is it something more, a structured data, for example? And what type of measure do I take for Y? So here is just the form of the teacher. So the replica computation works extremely well in this case, and as Florent has showed us, and as we've had many examples, this has been solved for a bunch of models using the replica method. And for example, convex models, if you ask Florent, he will tell you that they are too easy. They don't even break the replica symmetry. Now, just as we know, replica formulas are conjectures, and there's a big amount of work on proving replica formulas. Again, Florent has showed you the typical method that is used to do so is Gaussian interpolation, and so which originates in mathematical and statistical physics, Guerra and Toninelli, and later on by Talagrand. And in the context of machine learning, phase retrieval, and signal processing, there has been extensive work, so Jean Barbier and collaborators in the base optimal ID Gaussian case, and now Antoine, for example, for correlated Gaussian in the complex case, also in the base optimal setting. But now, the thing is that base optimal setting is perfect for signal processing when you have a perfect understanding of the measurement process or the device that you are studying. But for machine learning, it's good to say, okay, for example, maybe I'm doing a linear regression on a classification problem. I want to study what's the effect of a mismatch. Okay, and for the non-base optimal setting, actually, the Gaussian interpolation method is not is quite difficult to extend, and this brings us to another type of proof. So this brings us to another set of papers and literature which we could call asymptotic errors. And a good example to start with is a paper by Andrea Montanari and Moshe Bayati, where they said, okay, I want to study the reconstruction performance of the lasso with an ID Gaussian matrix. So how did they do that? So they used approximate message passing, which is this algorithm, which has been already mentioned by several of my colleagues. So the detail of the iteration, well, you're just forming an estimate z from the error between y and a given prediction at time t, a times x. And then you have this weird term, which in statistical physics is called the Onsager reaction term. Here the brackets stand for a component-wise average. And then you just update your estimate by, with a soft thresholding operation on the estimate you formed before. So what's so special about approximate message passing, and why did they use this algorithm? Well, again, as I'm sure you've heard before last week or during this week, it obeys state evolution equations, which have been rigorously derived again by Bayati and Montanari. And roughly said, the state evolution equations allow you to track exactly the asymptotic behavior of the iterates produced by AMP. So here I just remove the time indices for simplicity, but what they tell you, so z is a Gaussian variable, what they tell you is that the estimates produced by AMP, they are asymptotically Gaussians centered around the ground truth x0. And so with this, I mean, you can compute whatever you want. One of the nice things of this is that it gives you the same result as a replica computation when you take the fixed point of these equations. So basically, if I can find surely a convergent trajectory of this algorithm, then I have the asymptotic statistical characterization of the estimator I'm looking for, and this is what they did. Now, what's our goal? So for the non-base optimal problem, we would like to go beyond ID Gaussian data, do something a bit more, introduce structure in the data. And we would like to derive a proof which does not depend on a specific structure of the loss function. We'd like to say, can we handle in a modular way, in a modular way, the loss function and the regularizer. So what we'll be looking at is rotationally invariant matrices, which Marilou has already talked about yesterday. So if I take the singular value decomposition of the matrix, U dV transpose, I'll take U and V hard distributed. Actually, you don't really need U, only V is enough. And D contains singular values with an arbitrary distribution with compact support. And as far as the loss and regularizer, we'll allow any convex and separable G and F. Again, so this is built on replica intuition, which is more than 20, well, quite old, essentially notably by Yoshiyuki Kawashima in 2007, and a tiny bit later by Sandeep Rangan and collaborators. And they basically derived the replica formula for this type of matrices. And we're proving this conjecture along with with our work. So just a brief recap about what we know so far. So we'd like to prove asymptotic errors or replica formulas, which is equivalent to this setting. We'd like to go beyond the base optimal setting, beyond the ID Gaussian matrices, and do a generic proof for FNG. We know the Gaussian interpolation method does not really work well in this setting, but we have this family of algorithm, message passing, which have rigorous statistical characterization through these state evolution equations, and these state evolution equations are linked to the replica formula. So from then on, I hope the following sketch of proof will appear quite natural to you. So the key points, we'd like to build a sequence whose fixed point solves problem 1, a message passing algorithm. Then we'd like to have a statistical characterization of the iterates, which matches the replica prediction, state evolution equations. And then we'd like to ensure convergence of the sequence. Because if you do not ensure that the sequence that you build converges to the right estimator, you don't know what you are characterizing. You could have a divergent sequence, which actually is often the case when you are using message passing algorithms. Now, at the fixed point of this sequence, we'll have X star and statistical properties. How do we handle this? We'll use vector approximate message passing. Antoine has mentioned it already. It's an extension of vector AMP. It's an extension of AMP. We'll use the state evolution equations and study its convergence, basically. Now, the detail is not very important, but vector AMP is an extension of AMP, which handles these rotationally invariant matrices with arbitrary spectrum. But as you can see, there's a first step here which will handle. So this is for linear regression. This solves linear regression. There is a first step here which will handle the regularization, and the second step which will handle the nonlinear, the non-trivial, so the arbitrary eigenvalue distribution. And without any complicated things, you can see that it has the same structure as AMP. It's the same idea. You have an update, so a denoising, if you will. Then you have this Onzager correction. Again, here the bracket is the same as before, it's a component-wise average, and then an update. And it's the same thing for this one. And this algorithm also obeys rigorous state evolution equations, but here for any spectrum of a data, not just ID Gaussian matrices. For the generalized linear model, it's twice as big, but the idea is exactly the same. For the regularizer, I have an estimate, an Onzager correction term, and an update. Same thing for the nonlinearity of the loss. And for each of these two, I have a least square. So just here, the state evolution equations of the two guys I just showed you before are a little thick. And if you look at Kawashima's paper, for example, the replica equations are honestly even worse. It would be useless to show them to you now. I'd be happy to if you want to discuss later on. But trust me, you can match both of them. Several references for that. And to conclude, about convergence of the sequence, which is actually a huge part of the work. We just use convex analysis method because vector AMP and generalized vector AMP can be very nicely mapped with a few modifications to standard descent methods like proximal descent methods or alternative direction methods of multipliers. And then we use the classical convex analysis tools, determining Lipschitz constant of each of the operators composing the iterations, so how much does it grow for each iteration. Getting a hold of a good Lyapunov function, so this is especially for the generalized vector approximate message passing, which as you have seen is quite big. So here, bluntly studying the difference of successive iterates is not good. So one needs to find a function which is handier to study, and this is that's a Lyapunov function. So here it's possible to adapt control theory methods to generalized vector AMP to do so. And then use the geometrical properties of the landscape, again classical things like the strong convexity, to conclude. And what we found out is that for both vector AMP and generalized vector AMP, it's possible to build convergent sequences for sufficiently strongly convex problem, and this is enough to conclude the proof. And just before I close up, so I don't need to convince you that the replica worked very well, but as you can see, this is a finite size prediction, ID Gaussian data, a different eigenvalue distribution for ridge regression, support vector classifier, and logistic regression on a signed teacher, and the agreement is excellent for a few hundred points on the data matrix. Thank you.
Questions for Cedric? Thank you
Yeah, yeah, yeah.
So it means they are independent.
Independent, yes, yes.
And then the data matrix becomes
UDV transpose, yes.
So when does UDV transpose with U and VR
Represents role
have
dependent.
independent
Ah, okay. So this is a mistake on my part. You're right. With the UDV transpose, I mean it's not always row independent. I honestly don't know the exact mapping. I don't know.
For GOE it's true. So
Yeah, for GEO it's
it's an
true.
interesting question
Yeah.
to see what are
Yeah, I don't know. You can do row orthogonal matrices that are used a lot in signal processing by putting ones and zeros in the diagonal. Yeah. The idea, if you have a given data set, is that you can just take the deterministic eigenvalue distribution of the covariance matrix.
Speakers in the meantime, also. Last question while the speakers are switching. No? Good.
Can I put this in your pocket?
Yes.
This one? It's okay. It's okay. And this, I will pinch it somewhere. Great.
No.
Are you sure?
Yeah, right.
So the third speaker today is Mirko about expectation propagation for the diluted Bayesian classifier.
Okay. Hello everyone. All right, today I'm going to talk about, again, generalized linear model. And I'm going to focus on the expectation propagation algorithm as applied to the case of the diluted Bayesian classifier. Why doesn't it work? Anyway.
You can continue.
All right. Is it working? Yeah. All right. I'd like to give you some insight about how the expectation propagation algorithm, which is the one I used, work for this. No worries. Works can be applied to this program and how it works, how it does the inference. And then to conclude, I'll tell you about some comparisons that I made, and I draw some conclusions. Okay, it goes without saying that any comments or observations that you might have on this work are very, very welcome. And so feel free, even after the talk has ended or in the coming days, to come to talk to me if this interests you. All right, I start giving you some motivations, and on top of the theoretical motivations that make the problem interesting, because this is obviously a very nice playground for methods in statistical physics, and there are also other more practical motivations, if you wish, that might be more interesting from the data science point of view. So I think that everyone here will agree with me that in the past years, databases have grown a lot in dimensionality. And so one one problem is actually identifying what are the relevant features of a given data set. And this is a very important problem in machine learning. It goes under the name of feature selection. And I'm going to talk about this problem in the context of classification. And there are many applications for this. For instance, in bioinformatics, you might want to find what are the biomarkers that discriminate whether a given tissue is healthy or is cancerous based on gene expression data on a microarray. In computer vision, you often want to do image classification, and you want to understand which features allow an image to be classified in one way rather than in another way. And then there are many other applications. There's text classification, social media, and the list could go on. Okay, I'm going to go back to the teacher-student scenario that has been discussed a lot these days. As a simple example of a Bayesian classifier, I'm just going to consider a perceptron. It's actually a sparse perceptron. So we have a student perceptron which needs to estimate a classification rule that has been decided by a teacher with weights B, and these weights are diluted. Okay, and the teacher assigns labels and provides example to the student. Okay, these are things that you already know, but just to.
Is the teacher sparse as well?
The teacher is sparse, and the student doesn't know how sparse the teacher is. It might need to figure this information out on its own. All right. So, given the examples, the task of the student is to adjust its weights in order to learn the classification rule of the teacher. And I'm going to give you now a statistical mechanics formulation of the problem. Okay, let's go back to the teacher-student scenario, and let's focus on the student. The student has weights W, and this W have to satisfy two kinds of constraints. First of all, as the student knows that the teacher is sparse, there will be a dilution constraint on the weights of the student. And then there's a consistency constraint, because these weights need to satisfy the teacher rule. And this constraint can be cast in terms of a positivity constraint, as you can see there. And now, at this point, it's natural to define a linear estimation problem, introducing further auxiliary variables y, which are defined in terms of the left-hand side of the inequalities that are written there. And by definition, y will be the product of a matrix X sigma, which depends on the examples provided by the teacher. And then there will be the weights that need to be retrieved. You can write a posterior distribution for the set of variables w and y. This will be given by a likelihood that encodes the linear constraints, which, by the way, from the point of view of statistical physics, is nothing but the zero temperature limit of the Boltzmann distribution, where you have a quadratic form that is this energy function that encodes, that penalizes solutions that don't fulfill the linear constraints. And then you have priors on the variable as well. So you have dilution, a dilution prior on W, and you have a consistency prior on the Y variables. And now what you want to do is to estimate the weights using a minimum mean squared error estimator. So you are interested in the averages, but in general you're interested in marginals and higher moments, because, for instance, you want the variance on the weights. And so you need to take integrals over of this posterior distribution. Now, unfortunately, this posterior is intractable in the sense that these integrals are very difficult to compute, and therefore you need approximations. Now, the kind of approximation that I want to consider, as you might imagine, is expectation propagation, and I give you a very short introduction just to try to make sure that everyone understands what's going on here. As I said, we want a tractable approximation to the posterior distribution. I'm going to assume that the prior on the weights and the prior on the consistency variables as well is factorized over the variables. Now, expectation propagation. In expectation propagation, I'm going to tell you the formulation I'm most comfortable with. So it will be a Gaussian expectation propagation. You want to consider two kinds of approximation of the posterior. So one is a full Gaussian approximation, where you imagine that you're actually replacing each factor in this prior by Gaussian approximating factors that have some mean A and some variance dk.
I have a question. Are you assuming something on the x? You mentioned the y and w. Are you assuming something on the x? Like
X is known. X is known. X is known, and when I do the comparisons, I'll show you some simulations that are done in a variety of conditions where we pick specific examples of X.
But deterministic ones, not random.
No, they're random. So I'm going to consider patterns that are drawn from IID Gaussian distribution, a multivariate Gaussian distribution, and even binary patterns that are computed that arise from a Glauber dynamics at 0 temperature. But yeah, I'm going to show you what the results are in these cases later. All right, so this was the full Gaussian approximation of the posterior. So you replace all factors with Gaussians. And then you have also another kind of approximation. It's called leave one out distribution. It's the same as the full Gaussian approximation, but you keep one of the factors without replacing it with a Gaussian. So here I wrote psi. Depending on whether psi refers to the w or to the y, it's going to be a gamma factor or a lambda factor, where gamma is a sparsity prior and lambda is a consistency prior. Now, at every iteration, the expectation propagation update works like this. So for each variable, you fit the approximating Gaussian factor related to that variable, so that the Kullback-Leibler divergence between the leave one out distribution and the full Gaussian approximation of the posterior is minimized. That will give you the current estimate for AK and DK, which are the mean and the variance here of the Gaussian approximating factor. And if you write it down, you'll realize that this turns into moment matching conditions with respect to the full Gaussian approximation of the posterior at the leave one out distribution. Okay, this is what in this formulation for this problem the expectation propagation algorithm looks like. I don't really want you to understand it. I just want to focus your attention on the fact that here you need to compute the inverse of a covariance matrix. So this is the bottleneck of the method in terms of computational complexity, and therefore the complexity will be cubic in the number of weights for this problem. Okay, so as promised, I'm going to show you some results now with various kinds of patterns and possibly with noise. Okay, I'm going to start with a simple IID Gaussian distribution from which you draw the patterns. And here on the right, you can see a plot where you can see the mean squared error associated to the estimation of the weights by the student as a function of alpha, which is the number of patterns divided by the number of weights. And here I'm going to consider 3 algorithms. So one is EP, obviously, and then there's a variation of approximate message passing, for the 1-bit compress sensing problem, which, by the way, I didn't tell you, but is another way to state this sparse perceptron learning problem that I'm telling you about. And then an extension of vector approximate message passing to the generalized linear model. Okay, well, in the case of IID Gaussian patterns, you can see that there's not really a lot of difference between the performance of the 3 algorithms. So as I told you, we don't assume necessarily that the student knows the sparsity of the weights of the teacher. So in that case, we need to estimate it. So here I had a system with 128 weights, and 1/4 of them were non-zero. And this is the estimation by P as a function of alpha. And you can see that it's a pretty good estimate. Here you see the error, the relative error. And it improves as the training set gets larger, as you might expect. So, yeah.
That's a little, because if you did that with the 1-bit AMP, it should estimate the row consistently. So even for small alpha, it should give you 0.25 if you do it with expectation maximization. So I'm quite surprised that you actually see like a discrepancy.
I'm sorry, I think I'm not getting what you say. So these are related to EP.
Right, and if you compare to the other approaches, since we worked with the 1-bit compress sensing, if you learn the role with expectation maximization there, you actually learn it exactly up to the finite size calculations.
Okay, I didn't try that. I trust you. And so you're saying that it's up that you actually have some discrepancy between the true value and the learned value.
I'm surprised by that.
Okay. I'm not sure how to answer to that, but I mean, perhaps it's better to discuss about it later. Okay. So that was a simple example with IID, Gaussian patterns, and now I'm going to show you the case where we sampled them from a multivariate normal distribution with a suitable covariance matrix. And in this case, okay, 1-bit AMP didn't converge, so I'm not able to show you results for that. But I'm showing you a comparison between EP and generalized bump. And what you can see here, and which is kind of striking, is that as the number of patterns increases, there's a discrepancy between the performances of the two. And actually, you can see that expectation propagation performs better than generalized bump.
So which implementation of the generalized bump have you used?
I have used the one which is it's not the one from Rangan. It's called generalized. It's called a generalized framework for Bayesian framework for generalized linear models. It actually it divides the problem into 2 steps. That one is a minimum mean square error estimation, and the other one is an inner block where you do where you perform a VAMP or AMP on the standard linear model. It's I can give you the reference later.
Well, I'm also surprised by that because kind of the generalized bump as I know it, it's like the derivation you present. This is just one way to derive it, so I don't see much.
There's a difference, yeah.
What's the difference?
You invert the matrix. So I think what you're doing is that you're using variances which can be different for each one.
Yes.
Right? And if you do this, anytime you have to invert the matrix, you have to invert the matrix. So
so here I need to compute an inverse of the covariance matrix at each iteration, while in VAMP you do it only at the first step, and then you actually do all iterations without you compute an SVD at the beginning, and then you don't invert anything anymore.
Okay, so it's
This is more general. You could think to VAMP as a particular instantiation of EP under more restrictive conditions. In EP, we don't even assume that the kind of matrices that we consider are right orthogonally, are right rotationally invariant. As far as I know, there are no assumptions on the linear transformation matrix. But again, if you're interested, we can follow up later. All right, and here I'm also showing you that in this case, the vector approximate message passing had some troubles converging as the training set was increased in size. And okay, we wanted to understand a little bit why, where this discrepancy comes from. And sorry, by looking at ROC curves, we saw that, especially for large alpha, the feature selection properties of expectation propagation were actually better, as you can see from the ROC curves. And again, we tried to learn the sparsity or the density, if you wish, of the teacher. In this case, patterns are correlated, so there's less. There's less information, if you wish. So it's normal that the estimate is a little less accurate, but nonetheless, you can see that as you increase the number of patterns that you present to the student, the estimate gets better. We also tried some experiments with the noisy labels. So we set a probability that the labels is kept unchanged. I call it eta, and that's 90% in all the simulations I'm showing you from now on about this case. And we mislabel all other examples. The student doesn't necessarily know how many examples are mislabeled. Is it time?
yeah, already 5 minutes after.
It's okay. It's okay. I'll recap. So I'm going to conclude now. I just wanted to show you that actually, if you look at the areas under the curves, they're not very different for the two algorithms, but we're able to estimate the number of non-flipped labels, and so also the number of flipped labels, quite accurately in a variety of cases. And we compared it with an algorithm that is based on expectation maximization that learns expectation maximization as applied to both the weights and the noise. And
We should be concluding.
sure. And what I just wanted to show you is that that the training time is doesn't depend on the training set size for EP. I'm just going to go to the conclusions now. And okay, I hope that I convinced you that EP is a
We can go to the dinner. Bye-bye.
okay. I hope that I understood that I convinced you that it's an efficient learning algorithm. It's got good variable selection properties. We can learn online the dilution of the weights and the noise level. And overall, it's competitive both in terms of accuracy and of training times. Okay, we'll keep the questions for later, I'd say. Thanks. And apologies for going.